Let's then take a look at partition equilibria and relate it to solvent extraction. Let's consider why it's called an equilibrium. In any equilibrium situation, you will always find two opposing processes. In a chemical equilibrium, it will be the forward reaction versus the reverse reaction. In partition equilibria, we see two red arrows here representing the two opposing processes. The movement of a solute between two immiscible liquids. And this is how solvent extraction works, in fact. Solvent extraction is the partial removal of a solute from one solvent into another immiscible solvent. Consider the separating funnel here with the two immiscible liquids. The line here represented in red is the line between the two immiscible liquids, and it's known as the interface. So the solute will make its move across the interface between one liquid and the other. When it has reached a point of a dynamic equilibrium, the movement in one direction will exactly match the rate of the movement in the other direction. Organic compounds are frequently produced in aqueous solution, and these will generally be more soluble in organic solvents than in the water of the aqueous solution. You'll probably be familiar with the rule of thumb, like dissolves like. That's to say, polar chemicals dissolve in polar solvents best. Non-polar substances, typically organic substances are non-polar, dissolve best in non-polar solvents. In solvent extraction, an immiscible organic solvent is shaken with the aqueous solution containing the organic product. Emphasis, of course, on shaking, because if the two liquids are left to sit simply in the separating funnel as shown there, the only point of contact is the interface, and the transfer of the solute between one liquid and the other will be very slow. Shaking will mean that the equilibrium establishes much sooner. Ether is also known as ethoxyethane. It's the most commonly used solvent for extracting organic chemicals from aqueous solution. You can see its structure here. Two ethyl groups joined by an oxygen. When you look at the reasonable symmetry in this molecule, you can predict that it has a very weak dipole moment and is essentially a non-polar substance. That'll make it an excellent solvent for dissolving most organic substances, which are themselves non-polar. Now let's consider water as well. This is a water molecule. And water, of course, in view of its bent shape, and its two dipoles that don't cancel, is a polar molecule. Added to that, water molecules can form very strong dipole-dipole forces known as hydrogen bonds. In contrast, the ether molecules there at the bottom cannot form dipole-dipole attractions nor hydrogen bonds. They will be held together by much weaker attractive forces known as van der Waals forces. I'm using dashed lines here to show the hydrogen bonds that will tend to form between water molecules themselves. There are, of course, a range of different organic substances that do dissolve readily in water, and there'll be substances typically that can form hydrogen bonds with water molecules. They include ethanol, propanol, propanal, propanone, ethanoic acid, and ethylamine. Returning then to ether at the bottom, and indeed organic molecules in general, do bear in mind that all organic molecules are held together by van der Waals forces, as well as possibly other kinds of forces as well. And down at the bottom there's another chemical that you'll encounter in these partition equilibria questions. The green spheres represent chlorine atoms, so we have their CCl4 molecules, known either as carbon tetrachloride or tetrachloromethane. And you can reason from the symmetry of the molecules that they are non-polar, so the only type of attraction between CCl4 molecules will be van der Waals. Another example we'll encounter in these partition coefficient questions is trichloromethane, CHCl3. The molecule is not completely symmetrical, so there will be a very weak dipole moment in the molecules, So in addition to van der Waals forces, you'll have weak dipole-dipole attractions. And you see I've abbreviated that to TCM. Very important rule of thumb then, like dissolves like. So during solvent extraction, some or most of the organic product will move from the aqueous layer into the non-polar layer, in which it's more soluble. So if the lower layer here in the separating funnel is the aqueous layer containing the organic product, you'll shake it with an immiscible liquid in which the organic substance is more soluble. That way it will tend to move from the lower layer into the upper non-polar layer in which it's more soluble. It is, however, an equilibrium, and when the dynamic equilibrium establishes, it means that the rate at which the organic solute moves from the lower layer to the upper layer is exactly matched by the rate at which it moves in the reverse direction. Let's consider another partition equilibrium situation, this time iodine I2 between tetrachloromethane and water. You see the tetrachloromethane molecules there, CCl4, they're non-polar, and the question is, will the iodine be more soluble in the non-polar tetrachloromethane layer or in the water, the aqueous polar layer? So we need to consider whether iodine I2 molecules are polar or non-polar. In the bottom right you see the I2 molecules represented by purple spheres. Iodine molecules are relatively large molecules, but they are non-polar. Being large with a large number of electrons, they will have strong van der Waals attractive forces between them. But iodine molecules are non-polar, so they will be much more soluble in the tetrachloromethane, which is also non-polar, than in the polar water layer. So the iodine will partition itself between the water and the tetrachloromethane. Now, if these two liquids are present in equal volumes, one would expect that when the dynamic equilibrium has been established, much more iodine would be found in the upper layer, the tetrachloromethane layer. Here I'm going to consider an example where the iodine is entirely dissolved in water, represented by the green crosses here. And we take some pure tetrachloromethane, which is immiscible with water. It's less dense, so it floats on top. We put a stopper on the separating funnel, and then let's give it a good shake. Of course, the interface will disappear at this stage as the two layers mix through one another. I'm not showing that, I'm afraid, here. But the separating funnel would be shaken very vigorously. This enormously increases the surface of contact between the two immiscible liquids, and therefore the boundary at which the green crosses can transfer. That's to say, the iodine molecules can transfer from the polar aqueous layer into the non-polar carbon tetrachloride layer. And this is what it might look like when the dynamic equilibrium has been established. And you'll notice that most of the green crosses have transferred into the upper non-polar layer, most of the iodine in other words, but not all. And eventually an equilibrium will be established, a dynamic equilibrium. The green crosses will still continue to move from the bottom layer into the top layer, but they'll be moving from the top layer into the lower layer at the same rate. So there's no point in continuing to shake it. You're not going to get any more of those green crosses, any more of that dissolved iodine to move from the water into the carbon tetrachloride. You just have to stop at that point, remove the stopper at the top, then open the tap and run out the lower layer, retaining the upper carbon tetrachloride layer. Then the carbon tetrachloride layer would be transferred into a beaker, and the lower aqueous layer would be returned to the funnel. You see the lower aqueous layer there represented in the beaker on the right. And fresh tetrachloromethane would be added to the funnel, and the funnel would be shaken once more, so the process is repeated, and that would extract even more of the iodine from that aqueous layer. Not all of it, but a good deal more of it. Why is ether used in particular? Why is it the most commonly used solvent for extracting organic chemicals? Well, because it dissolves most organic compounds. It can be easily removed after extraction by simple distillation owing to its low boiling point, around the temperature of blood to 37 degrees C. But there are a few warnings when using ether. Ether is highly flammable, so you'll have to avoid having naked flames in the laboratory at the same time. And ether is known to form peroxides when exposed to sunlight, and peroxides are explosive when heated. For that reason, it should be stored in a brown bottle in a fridge. And as you're probably aware, ether vapor has anesthetic as well as toxic actions on the human brain. So for that reason, during the transfer of ether, it's best to use a fume cupboard. Okay, the first of several questions now. Do pause and give each of these a go, please, before you look at my solution. Highlighted in blue here, it states in trichloromethane than in water. Now, the order in which these chemicals appear in that sentence is very important. Because trichloromethane is mentioned before the water, then we are to assume that X is 12 times more soluble in the trichloromethane. Just read that first sentence again, and the order in which trichloromethane and water appear is very important. It means, because trichloromethane comes first, before the water, it means that X is 12 times more soluble in it. That's to say that when the dynamic equilibrium has been established and X has partitioned itself between the two immiscible liquids, the concentration of X in the trichloromethane will be 12 times greater than in the water. And note, we are talking about concentration. That's what the square brackets represent there, concentration of. Concentration of X in TCM is trichloromethane, concentration of X in water. And that's another way you could express it, that the concentration of X in TCM over the concentration of X in water is 12 over 1. Now let's return to the idea, the important principle in fact, that this is another equilibrium situation. And we could represent and should represent what's going on here by expressing it as an equilibrium equation. It is, of course, a physical rather than a chemical equilibrium situation, but we can apply exactly the same equilibrium rules. Notice that I've reversed the equilibrium equation here to show X going from the water or aqueous layer into the trichloromethane layer, like we had in the example in the separating funnel a few moments ago. So you can write an expression for this equilibrium when it's reached a dynamic equilibrium. And Kc will be the concentration of X in the TCM, the product so to speak, over the concentration of X in the aqueous layer or water. And we've been given in this question that it has a value 12. So that in fact is what the partition coefficient is. It's actually an equilibrium constant for that equilibrium. So instead of calling it Kc, we can call it Kpc, where Pc stands for the partition coefficient. And do remember that since it is an equilibrium constant, the partition coefficient is a constant at a particular temperature. So it'll usually be given as the partition coefficient at room temperature. And so returning to the question to pick up the rest of the information, you see there that we've got a total of 25 grams of X, which will partition itself between the water and the trichloromethane. It's initially present in the 1 cubic decimeter of water. You're being asked to find out what mass of X will be extracted. That's to say, what mass of X will end up in the trichloromethane layer. I would suggest here that you use a variable such as m to represent that mass, the mass of X that ends up in the ether. And since you begin with 25 grams of X, that means that the mass of X left in the water will of course be 25 minus m. And so we've got all the information really that we need, including the volumes of the two solvents, 1,000 cubic centimeters of water and 100 cubic centimeters of trichloromethane. So let's return then to the expression for the equilibrium constant or partition coefficient that's given. And there you have it. The concentration of X in TCM over the concentration of X in the aqueous layer is 12. Now, how do we normally express the concentration of a chemical? Well, as moles per cubic decimeter, or moles dm to the minus 3. But actually, so long as we express the concentration on the top line and the bottom line in the same units, it will be okay because the units will then cancel. So when it comes to these partition equilibria questions, we don't express the concentration as moles over cubic decimeters. Notice that we've been given a mass, albeit presented as m and 25 minus m, and we've been given cubic centimeters of the two liquids, immiscible liquids. So in fact, in these questions, we express the concentration as the mass over cubic centimeters rather than cubic decimeters. So the mass will either be m or 25 minus m, and the cubic centimeters, well, in one case we had 1,000 cubic centimeters of water, and in the other 100 cubic centimeters of the trichloromethane. So there we have it. We just have to put all of these figures into that expression. So let's go on and do that now. So we can express the concentration of X in TCM as its mass m. Remember, we assigned m to represent that mass of X extracted into the TCM over the volume of the TCM, which was 100 cubic centimeters. And do the same then with X in the aqueous layer. The mass was 25 minus m over the volume of the water, 1,000 cubic centimeters. And all we need now is to solve that. Okay, and in go the numbers. We have m over 100 divided by 25 minus m over 1,000 equals 12, or 12 over 1. To solve this, we cross multiply. That times that equals that times that. So we have m over 100 times 1, which is m over 100, equals 12 into 25 minus m over 1,000. We can divide both sides by 100, so 100 divided by itself is 1, 1,000 divided by 100 is 10. So we have m equals 12 into 25 minus m over 10. Multiplied out the brackets there, 300 minus 12m. Multiply both sides by 10 to get rid of that 10 on the right. So you end up with 10m equals 300 minus 12m. Add 12m to both sides to get rid of the minus 12m on the right, so you get 22m on the left equals 300. Divide both sides by 22. I'm sure this is all easy for you, but just in case it isn't, showing you step by step what's done. And you end up then with m equals 300 over 22, which is 13.64 grams. And here's your next question to pause and have a go. This time the solute is butane dioic acid, and the two liquids are the ether, ethoxyethane, and water. We can use the abbreviation BDA for butane dioic acid. This is what it looks like. It's a 4-carbon organic compound with carboxyl groups there, COOH groups at either end. Butane dioic acid. So that's the solute, which will partition itself between the two immiscible liquids, the ether and the water. So try picking up the information that you need here, and then begin by writing an expression for the partition coefficient. And remember, it's very important to note the order in which the two liquids appear in the sentence. Between ethoxyethane and water is 5. So what does that mean? The mass of the solute is 5 grams. Now this can be confusing where you get two numbers the same in the question, and here you've got two 5s. One's referring to the partition coefficient and the other's referring to the mass of solute. So just be careful with those numbers that you're going in and picking the correct number. If they're similar, one might be 4 and the other 5, for example. So a common mistake is for the student to pick the wrong number. Anyway, again, we'll use the same idea. Assign m to the mass of butane dioic acid that ends up in the ether, because that's what we're being asked, to find the mass of butane dioic acid that will be extracted, in other words, into the ether. And since we start with 5 grams of BDA, then there'll be 5 minus m grams left in the water. So there's the expression, changing from moles divided by dm cubed to mass divided by cm cubed. And so we're left with m over 10 divided by 5 minus m over 100 equals 5 over 1. And we cross multiply again. That times that in blue is equal to that times that in green. So it's m over 10 times 1 equals 5 times 5 minus m over 100. We can divide both sides of that expression by 10 to get rid of the 10 on the left. And that should leave us then with what? M on the left hand side and 5 into 5 minus m over 10 on the right hand side. So multiplying out the brackets, 25 minus 5m, and we can solve that then. Multiply both sides by 10, get rid of the 10 on the right hand side. So we have 10m equals 25 minus 5m. Add 5m to both sides. We end up with 15m equals 25. M is 25 over 15, which is 1.67 grams. 1.67 grams of the BDA extracted by the ether. Again, pause and have a go at this next question. The first thing we identify then is the order in which the two liquids appear in the sentence. Ether before the water. So if the partition coefficient is 20, that means it's 20 times more soluble in ether than in water. The mass of solute 5 grams, and here we're required to work out what mass of X remains in the aqueous layer. Normally we're looking at the mass of X extracted into the ether, so we have to be careful to check what's actually being asked for, and in this instance, unusually perhaps, it's asking for the mass of X that remains in the water. I've still decided to stick with referring to the mass of X extracted into the ether as m, and given that we have a total mass of m grams to begin with, that means 5 minus m grams will be left in the water. So if you've noted the volumes of the two liquids, 250 cubic centimeters of water and 100 cubic centimeters of ether. So let's put those values in. I've elected that the mass extracted into the ether be m, 5 minus m, the mass then left in the water. I put in the volumes of the two liquids, and the partition coefficient is 20. So cross multiply again. M over 50 times 1 is equal to 20 times 5 minus m over 250. Now you can reduce this down. I've written divide again by 10, but actually I should be saying multiply both sides by 10. And it reduces it down to m over 10 equals 20 into 5 minus m over 25. Again here, because of the nature of fractions on both sides, it's simplest I think to cross multiply. So m times 25 equals 10 times 20 times 5 minus m. I've worked that out then. 25 m equals 1000 minus 200m. Add 200m to both sides and you're left with 225m equals 1000, and you can see m turns out to be 4.44 grams. Now that's, remember, the mass extracted by the ether, so 5 minus 4.44 or 0.56 will be the number of grams of the original 5 grams that will be left in the water. Okay, on we go. Pause and have a go at this next question. So here the solute is Y, and it's going to be distributed between, once again, ether and water. Now this time you're going to have to find the partition coefficient, and you've been given information to allow you to work out the concentrations of Y in the two different immiscible liquids. So let's put the information into the standard formula. So do notice that we want the partition coefficient of Y specifically between ether and water, and for that reason, because of the order of the two liquids in the sentence, we want ether on the top line. So I've simply put in the values there that's given in the question. 4 grams of Y dissolved in ether over the volume, 50 cubic centimeters of ether, and 1 gram of Y dissolved in the water, volume of water 250 cubic centimeters. Now you probably know how to solve this kind of calculation where you have a fraction over a fraction, and there is a basic rule in maths where you have a fraction divided by a fraction. What you do is you invert the divisor and multiply. Let me give you an example of this, and sorry if you already know this, but the way it works is this. Let's take an example that's easy to see. If we have a quarter divided by a half, now you may be aware that if you divide something by a half, it's the same as multiplying by 2. But anyway, a quarter as a decimal is 0.25, and a half as a decimal is 0.5. So what's 0.25 divided by 0.5? Again, dividing by 0.5 is the same as multiplying by 2. So 0.25 divided by 0.5 comes out to be 0.5. And I can show you then that this does work, what I said, that if you invert the divisor you can change it to a multiplication. So I invert the divisor, that's the fraction on the fraction below the line. So I invert a half and I get 2 over 1. So instead of having a quarter divided by a half, we can have a quarter multiplied by 2. And so on the top line 2 times 1 is 2. On the bottom 4 times 1 is 4, so you have 2 over 4, which is a half. So that's all I've tried to do there, is illustrate that it works. What you do then is to change it from a fraction over a fraction, invert the fraction or divisor on the bottom line, and then change it into a multiplication. So that will be 4 over 50 times 250 over 1. And that comes out, as you see, to give us a partition coefficient of 20. That's it. Now in this next question I'm going to involve moles. In order to test any physical chemistry aspect well, one should always incorporate moles. And here I incorporate moles by way of titrations. And you'll have to use your knowledge of titration calculations to work out the concentration of the organic acid in each of the two immiscible liquids. Do note that you're working out the partition coefficient for the acid between specifically the ether and water. Ether appears first in the sentence, so it'll be on the top line. You've got the volumes of the two immiscible liquids, 50 cubic centimeters of ether, 500 cubic centimeters of water. Now those volumes in fact are redundant, and it's important we take a moment to underline why. You're familiar now with the formula for working out the partition coefficient, and you'll be aware that what you need then is the concentration of the solute in both immiscible liquids. And in this case you're going to be able to work out the concentration of the organic acid, the solute, from the titration data. So in other words, those numbers, those volumes 50 and 500, have already been number crunched into the titration calculation, so they are redundant, they won't be used. You can see from the question 2 titrations have been carried out. In each case they've taken 25 cubic centimeters, presumably with a bulb pipette, and transferred it to a conical flask, as you see there on the right, and they've titrated it with sodium hydroxide solution. For some reason the concentration of sodium hydroxide is different in the 2 titrations. So we'll use these figures now to calculate the concentration of the organic acid in each of the 2 immiscible liquids. In any titration calculation, I'm sure you will be aware, there are 3 basic steps. The first step is to use N equals CV to calculate the number of moles of chemical dispensed from the burette. In this case, it's the sodium hydroxide. When you've worked out the number of moles of sodium hydroxide dispensed, you can use the balanced equation between the 2 chemicals to work out the number of moles of organic acid present in the conical flask. Now the equation here, I'm going to assume that the acid is a monobasic acid, something like ethanoic acid, and 1 mole of that monobasic acid will react with 1 mole of sodium hydroxide. So they react, in other words, in what we call or equimolar amounts. So in fact in this case it's relatively or very straightforward. The number of moles of organic acid in the conical flask will be exactly the same as the number of moles of sodium hydroxide dispensed. And finally, the third step in any titration calculation is to use your N equals CV equation again, but rearrange it so that you've got C equals N over V. And in the conical flask now you know the number of moles, you've just worked it out in step 2, and you know the volume, in this case the volume of the liquid added to the conical flask, which was 25.0 cubic centimeters for both immiscible liquids. Note, however, that in this expression V, the volume must be given in cubic decimeters. So divide your cubic centimeters by 1,000 to change it into dm cubed. That way you end up with mole divided by dm cubed, moles per cubic decimeter. So if you haven't already done so, work out the concentration of the organic acid in the ether and aqueous layers. Alright, the ether first of all, so we want to use N equals CV. C is the concentration, which is the concentration of the sodium hydroxide, 1.0. Times the volume, remember change the volume from cm cubed to dm cubed by dividing by 1,000, so it's 0.0225. And that gives us the number of moles of NaOH as 0.0225. Reminder of the equation, which we need to work out step 2 of the 3 steps, and it shows the reactant equimolar amounts. The number of moles of acid will be the same as the number of moles of sodium hydroxide dispensed, so that's 0.0225. Lastly, we use N equals C over V, rearranged to give us C equals N over V, and we must remember to put the volume in as dm cubed. The number of moles of acid, 0.0225, and the volume used in the titration, that's the volume of ether containing the acid, 0.025 dm cubed. And the concentration of the acid in the ether, as you see, turns out to be 0.9 mole per cubic decimeter. And so we go on now and do exactly the same thing for the aqueous layer. Again, they've taken 25 cubic centimeters from the aqueous layer, transferred that to the conical flask, added an indicator, suitable indicator for what is a weak acid and a strong alkali would be phenolphthalein, which would appear colourless in the acid and turn pink at the end point. And then in terms of N equals CV, the concentration 0.100 and the volume 9 cubic centimeters. Now the 9 cubic centimeters divided by 1,000 to change to dm cubed, of course, and you see that comes out as 0.0009 moles of sodium hydroxide dispensed from the burette. Again, they react in equimolar amounts, that is the sodium hydroxide and the organic acid. So the number of moles of acid present in the flask this time is 0.0009 moles. We rearrange the equation N equals CV, so we have C equals N over V, and we put in the number of moles, 0.0009, and divide by the volume. 25 cubic centimeters is 0.025 dm cubed, and the answer then 0.036 mole per cubic decimeter. That's the concentration of the acid in the aqueous layer. So we have both concentrations now to put into the formula to work out the partition coefficient. Concentration of the acid in the ether was 0.9 mole per cubic decimeter, and in the water 0.036 mole per cubic decimeter. So we put those into the equation for the partition coefficient, or KPC. And remember, the order in which they came in the sentence was between ether and water. For that reason then we must have the figures for ether on the top line. So it's 0.9 divided by 0.036, which gives us a partition coefficient of 25. And by way of stretching you just a little bit further, the next question also involves a titration, but this time it's a redox titration rather than acid-base. So take your time, take the information and give it a go. So iodine is the solute this time, which will partition itself between tetrachloromethane and water. The titration will involve a reaction between sodium thiosulfate and iodine, a redox reaction. Sodium thiosulfate will be the titrant in the burette, and fresh starch indicator would be used. You've been given information from two titrations. In the first, 25 cubic centimeters was removed from the aqueous layer and required 6.7 cubic centimeters of 0.055 molar sodium thiosulfate. With regard to the organic solvent tetrachloromethane, again 25 cubic centimeters appears to have been removed, and require 27.2 cubic centimeters of 1.15 molar sodium thiosulfate. And your task once again is to calculate the partition coefficient, this time for iodine between specifically water and tetrachloromethane. So here we have water appearing first in the sentence, so the concentration of iodine in the water will have to appear in the top line. So once again we go through those three typical steps for any titration calculation. We'll work out the number of moles of sodium thiosulfate Na2S2O3 dispensed from the burette using fresh starch indicator. From that we'll then have to look at the balanced redox equation and work out the number of moles of iodine present in the flask, and then thirdly work out the concentration of the iodine in the solution in the flask. So it's a redox reaction. The best way to arrive at a balanced redox reaction is to take a look at the two relevant half equations which you see here. In the first one you see iodine undergoing reduction, 1 mole of iodine requiring 2 moles of electrons. I've already reversed the second half equation to show it as in fact an oxidation, and you'll see most importantly that it also involves 2 moles of electrons. So we can simply add the two left hand sides together and the two right hand sides together, and the electrons will then cancel. So that's how I've come up with that balanced redox equation. And the important thing is that 1 mole of I2 is seen to react with 2 moles of the sodium thiosulfate. Think about that. Whatever number of moles of sodium thiosulfate is dispensed from the burette, what does that tell us about the number of moles of iodine? Well, according to the balanced equation, there will be half as many moles of I2 as moles of S2O3, sodium thiosulfate, used. So when we worked out part 1, the number of moles of sodium thiosulfate dispensed, in part 2 we'll half that to get the number of moles of iodine present in the flask. So here you see I'm looking at the tetrachloromethane layer, TCM, and I'm using N equals CV. I'm putting in the information, concentration 1.15, the volume changed from cm cubed to dm cubed, and that gives us 0.0313 moles of sodium thiosulfate dispensed. The number of moles of iodine, again according to the balanced equation there at the top, will be half as many moles, so 0.0156 moles of iodine in that 25 cubic centimeters. And the third typical step then is to work out the concentration of the iodine by rearranging N equals CV to get C equals N over V, put in the number of moles and the volume in dm cubed, and there's the answer, 0.626 mole per cubic decimeter. That's the concentration of iodine worked out in the tetrachloromethane layer. Just repeat that now using the figures given in the question for the titration involving the 25 cubic centimeters from the aqueous layer. In go the figures, and you can see there the number of moles of thiosulfate dispensed. The number of moles of iodine will be half that number, again referring to the balanced equation at the top of the page there, top of the slide. And using C equals N over V, we put in the figures, and that gives us the concentration of iodine in the water or aqueous layer as 0.00736 molar or mole per cubic decimeter. So we now have the concentration of the iodine in both the TCM and the water. Recall the order in which the immiscible liquids came in that important sentence, and it was water that was mentioned first. So there's the concentration of the iodine in the water, 0.00726, and in the TCM 0.626. Between water and ether, so the water concentration, or the concentration of the iodine in the water, goes in the top, 0.00736, and the concentration of the iodine in the ether, 0.626. And there's the partition coefficient, or KPC, 0.0118. Now I come finally in this video on partition equilibria to take a look at one extraction versus several extractions. And you're going to see here that you get more extraction if you use a given volume, not in one go but in several goes. So, and that will be illustrated by this question. So pause and give it a go. Prove this for yourself. Okay, let's extract the information then. You'll note to begin with that we have not been given the partition coefficient. But notice an important word there, I suppose, in the second line, equilibrium, that the solutions mixed here, the water and the ethereal or ether solutions, have been allowed to reach equilibrium. And we've been given the masses of X present in those two separate layers at equilibrium. 5 grams of X in the water layer or aqueous layer and 80 grams of X in the ether layer. Now from this we'll be able to get the concentrations of X in the two layers, the water and the ether layers, from which we can get the partition coefficient or KPC. Then when we've got the partition coefficient we can begin to work on parts A and B. We'll work out how much would be extracted by the ether if the ether was used in one go, simply 50 cubic centimeters of the ether in one go. And then we look at it in two stages using 25 cubic centimeters in ether, in other words the same total volume, but in two separate stages rather than in one stage. So let's get off and running here and use the information in the first three lines to work out the partition coefficient. So we're going to work out the partition coefficient for X between ether and water. So ether appears on the top line here. So you want the mass of ether over the volume of ether, and so that's 80 grams over 100 cubic centimeters. And the mass of X in water, 4 grams over the volume of water, 25. So we have a fraction over a fraction, and you'll recall one way of doing this is to invert the divisor and multiply. So that'll be the same as 80 over 100 multiplied by 25 over 4. Let's see what that gives us. 5. So we've established that the partition coefficient, which is an equilibrium constant, is 5. And so long as the temperature remains constant, that will remain the value for the partition coefficient for this particular scenario. So that's what we'll use now in parts A and B, the partition coefficient 5. So we begin by using 50 cubic centimeters of ether. And we're dealing specifically with 5 grams of X present in 100 cubic centimeters of water. So again we will assign the letter M to represent the mass of X that's extracted by the ether, so that's M, and the volume of ether 50. The mass of X left in water will be 5 minus M over the volume of water 100, and that has a partition coefficient of 5, we've just established that, or 5 over 1, so you cross multiply, you may recall, so that gives us M over 50 times 1 on the left hand side, and 5 times 5 minus M over 100 on the right. We can reduce that down by multiplying by 50. That gives us M on its own on the left, and 5 into 5 minus M over 2 on the right. And just follow your way through and you can see there M turns out to be 3.57 grams of X. So if you use 50 cubic centimeters in one go, 50 cubic centimeters of ether extracts 3.57 grams of the 5 grams. So that's quite a lot. Now let's do it with two separate extractions, twice 25 cubic centimeters, and see if we get more or less extracted. So you see here I've put in the information M over 25 rather than M over 50, and 5 minus M over 100 equals 5. And just go through the same set of steps, cross multiply, so you have M over 25 this time equals 5 into 5 minus M over 100. Multiply both sides by 25, you're left with M on the left and 5 into 5 minus M over 4 on the right. Multiply both sides by 4, you get 4m equals, and then multiply your brackets out, 5 times 5, 25, minus 5m. Add 5m to both sides, get rid of the minus 5m on the right, you're left with 9m equals 25, so m is 25 over 9. So with the first 25 cubic centimeters, the mass of X extracted of the 5 grams is 2.78 grams. It's important though to establish how much is left in the water, because we're going to take that water, put it back into a clean funnel and repeat the process with the second 25 cubic centimeters of ether. So 5 minus 2.78 grams, so 5 minus 2.78 grams That leaves 2.22 grams behind in the water. And that water with the 2.22 grams then is put back into the separating funnel and washed again with 25 cubic centimeters of ether. And you see here that I've put the figures back in. I've changed now from 5 minus m to 2.22 minus m to reflect the new mass of X present in the water. Go through the same set of steps. Multiply both sides by 25. You're left with m equals 5 into 2.22 minus m over 4. And proceed through it and solve for m. And m turns out to be 11.1 over 9. So using the second 25 cubic centimeters, you extract 1.23 grams of X. So we'll have to sum up those two masses that have been extracted by the two sets of 25 cubic centimeters of ether. 2.78 grams using the first 25 cubic centimeters and 1.23 in the second. A total of 4.01. So dividing the ether into two sets of 25 cubic centimeters extracts more, 4.01 compared with 3.57 grams. What would happen if we were to use 5 sets of 10? Well, from what we've seen, we would expect it to extract more. This is from a spreadsheet that I produced. You may find it present here on YouTube or on my website, using 5 sets of 10 cubic centimeters of ether. So I've put the information into the spreadsheet here. 10 cubic centimeters of ether, the partition coefficient 5, the volume of water 100 cubic centimeters, and the mass of solute 5. Now the first 10 cubic centimeters, the spreadsheet works out that it would extract 1.667 grams of X. That's in the first of 5 goes. And in pink there are 3.333 grams left in the water at that stage. Then the second set of 10 cubic centimeters, you can see it removes 1.111 grams with 2.222 grams at this stage left in the water, and in yellow 2.778 grams in total extracted into the ether. The third 10 cubic centimeters of ether extracts 0.741. Seems to be a mistake in yellow there. Disregard that. The fourth goes 0.494, and the fifth and final 10 cubic centimeters 0.329. So you sum those figures up, and in yellow you had the value there, but summarizing again, there's the second go, the third go, the fourth go, and the fifth go. And we've extracted a grand total of 4.34 grams. So how does that compare with using 50 or two sets of 25? Well, if you use 5 sets of 10, you get 4.34 grams of X extracted using 50 cubic centimeters. If you used 50 cubic centimeters in one go, 3.57, and two sets of 25, 4.01. So you see, if you split it up into 5 sets of 10, you extract considerably more. Okay, that's it. I hope that you've learnt about your partition equilibria and can apply it to solvent extraction. Thanks for listening.